Success doesn't happen by accident. It's built on hard-earned lessons soaked in sweat and failure. And no one understands this better than SpaceX. After every flight, they don't spend long celebrating. Instead, they dive straight into analysis, learning, and upgrades. That relentless drive is exactly why they lead the aerospace industry. Flight 9 has just wrapped up, and in its wake, it left behind both new challenges and valuable opportunities. So the question now is, what will SpaceX do to turn these lessons into future victories? A single tiny leak sent the entire vehicle spiraling through a sea of plasma. And that was just one chapter in the nightmare, known as Flight 9. This is Space Now, where we break down every heart-pounding second of spaceflight. Did you catch Flight 9 on May 27th? What a spectacle, right? Its success gave us reason to celebrate, but the close calls reminded us that the path to Mars is still paved with uncertainty and risk. And now, with Elon Musk announcing an ambitious launch cadence of one flight every 3 to 4 weeks, all eyes have turned to Flight 10, the next major milestone in SpaceX's high-stakes space race. To maintain that blistering launch pace, SpaceX must tackle every unresolved issue from Flight 9 head-on. Let's start with Super Heavy, specifically booster B-14, which suffered a serious failure during its landing phase. Just seconds before touching down on the ocean, an airborne explosion brought its journey to a sudden, fiery end. What really went wrong? Post-flight data and mission analysis trace the failure back to an extremely steep descent angle part of a new approach being tested to save fuel. But that sharp trajectory generated intense lateral forces along the booster's body, exceeding its structural limits. As a result, the core structure of B-14 either fractured or separated, leading to a fuel leak and ultimately igniting the remaining propellant. This poses a tough engineering challenge for SpaceX. How do you strike the right balance between aggressive performance and long-term hardware durability? There are two main paths forward. One is to revert to the mechanical catch method using the launch tower's arms, a technique that proved successful during Flight 7 when the booster was recovered fully intact and prepped for rapid reuse. If SpaceX brings that method back for Flight 10, it would offer better protection for ground infrastructure and help keep the launch schedule tight, even if it means sacrificing the potential fuel savings that come with steeper, riskier descents. If SpaceX doesn't fix this issue before Flight 10, the entire Starship program could be at risk. Here at Space Now, along with all of you, we're counting down every second. The second path forward is more experimental. Continue testing steep descent landings, but only over the ocean. This strategy minimizes the risk of damaging the launch pad and ground infrastructure. If SpaceX chooses this route, they'll likely assign the test to a previously flown booster like B-15, or possibly use a brand new one to preserve hardware that's already been flight-proven. What do you think they should do? With each ocean landing trial, SpaceX engineers will gather crucial data to refine descent guidance algorithms, improve structural design, and reinforce critical components. These incremental upgrades are essential if boosters are to survive increasingly aggressive landings, a non-negotiable step toward making Starship viable for future Moon and Mars missions. Both options have their advantages. The tower catch method helps maintain launch cadence and hardware turnaround speed, while high-angle ocean tests pave the way for significantly better fuel efficiency. The final decision will hinge on how much risk SpaceX is willing to accept the current workload at the launch complex and how ready their operations teams are under the pressure of a tightening flight schedule. Whichever route they choose, a clear plan must be finalized at least several weeks before Flight 10. That gives the teams enough time to modify flight software, update procedural checklists, and implement any necessary hardware upgrades. Do you think they'll be ready in time? But the descent profile wasn't the only issue Flight 9 exposed. It also revealed a critical weakness in the Raptor engine ignition system. One of the engines, specifically one equipped with a sensor ring, failed to reignite during the landing burn just moments before the explosion occurred. And as you may know, reigniting a Raptor engine after multiple in-flight cycles, when the fuel has already cooled, is one of the toughest technical challenges Starship faces. Extreme temperatures in the igniter feed lines, constant thermal expansion and contraction, and mechanical stress from engine gimbaling all contribute to the gradual wear and degradation of the Raptor's ignition system. To address this, SpaceX must continue building on the improvements introduced after Flight 8, including better thermal insulation and optimized fuel flow paths. But that alone isn't enough. How do you avoid disaster when a failed ignition happens just seconds before touchdown? A near-undetectable technical flaw almost destroyed the entire vehicle. Was it just bad luck? Or is the system warning us of something deeper? Space Now is breaking it all down right now. One possible solution is to add a redundant ignition system, potentially an auxiliary spark plug that kicks in if the primary igniter fails. What do you think? Should every engine have a built-in backup ignition layer? In the weeks leading up to Flight 10, SpaceX's ground test, teams will have to run dozens of ignition cycles on flight-configured Raptor engines. These tests will simulate extreme cold high vibration and intense pressure mirroring real-world mission conditions. It's the only way to find the breaking point for reliability. In automated test rigs, ultra-cold propellant will be pumped through a stationary Raptor engine while sensors record every millisecond of data pressure, temperature, and spark plug behavior. These hyper-detailed ignition signatures down to every flicker of a spark will help engineers pinpoint exactly when and why performance starts to degrade. Now, let me ask you this. If you had to bet on a spark plug to save your rocket in the freezing vacuum of space under tens of thousands of pounds of pressure, which one would you trust? From that data, the engineering team will be able to select better heat-resistant materials, redesign the ignition assembly, and rewrite flight control software to automatically adjust when sensors detect anomalies. In the long run, the Raptor 3, built with a high-content refractory metal architecture, is expected to handle harsh conditions much more reliably and could be the ultimate solution. But for now, fine-tuning the current system remains the top priority. Running parallel to ignition upgrades is another bold test validating fault tolerance during landing. SpaceX is preparing to conduct a final landing burn using just 2 engines instead of 3. The concept is to intentionally shut down one of the 3 center engines, proving the booster can still land safely with 1 engine out. But this only works if all 3 engines meet an almost perfect reliability standard. So here's the question. Would you bet a multi-million-dollar rocket on that kind of test? For Flight 10, SpaceX will most likely conduct this 2-engine burn over water first, before attempting a tower catch once they've gained enough confidence in the maneuver. Each of these test flights pushes the booster closer to the day, when full reusability from liftoff to catch becomes the norm, not the exception. However, while Super Heavy's upgrades rely mostly on booster test data, Ship 25 is grappling with far more complex challenges. During Flight 9, observers spotted small fires on the vacuum engine fairing and the lower skirt trouble areas that had already been flagged during Flight 8. But are these just minor flare-ups, or are they early warnings of a much larger threat? Fire might look spectacular to onlookers, but for a multi-billion-dollar spacecraft like Starship, it's a silent predator. These flare-ups can originate from Raptor exhaust plume impingement microleaks in pressurization or hydraulic lines, or the unintended ignition of aerodynamic heater elements. While the small fires seen during Flight 9 didn't immediately compromise flight safety, they exposed a serious vulnerability. Starship is still highly susceptible to stray flames. So what's the fix? Ahead of Flight 10, SpaceX needs to install additional ablative thermal shielding or insulated cladding around the joints between the engine section and the fuselage. They might also consider applying fire-resistant coatings to the vehicle's exterior, similar to the heat-protective paints once used on the U.S. Air Force's AGM-86 cruise missiles to improve survivability in high-temperature environments. Do you think SpaceX should adopt this military-inspired tactic? Looking further ahead, integrating ultra-sensitive fire detection sensors connected to localized CO2 or water mist nozzles could allow any spot fires to be extinguished within moments of ignition. The additional weight from such a system is minimal when compared to the enormous benefit near-zero fire risk across rapid reuse cycles, a core goal of the Starship program. But for Ship 35, fire wasn't the deadliest threat. It was space itself, cold, vast, and unforgiving. After main engine cutoff SECO during the unpowered coasting phase before atmospheric re-entry, the vehicle lost attitude control. What followed was a violent, uncontrolled spin that turned re-entry into an all-out nightmare. Instead of presenting its windward heat shield as designed, Ship 35 tumbled uncontrollably, exposing its sides, structural joints, aft flaps, and hinge points directly to the searing plasma environment. When communication was briefly restored, on-board cameras captured a sobering image. One of the aft flaps had been partially scorched. It wasn't just physical evidence, it was a warning loud and clear for every aerospace engineer watching. The violent spin triggered massive vibrations throughout the vehicle, threatening the integrity of fuel lines, avionics racks, and structural welds. How could a machine this advanced lose control so catastrophically? Elon Musk pointed to the root cause, a loss of pressure in the main propellant tank. A fuel leak had allowed either cryogenic propellant or the pressurizing ullage gas to escape, dropping tank pressure below the threshold needed to sustain both the engines and attitude control thrusters. Once the thrusters lost power, the vehicle could no longer maintain its orientation, and that's when the fatal spin began. Did you know that a single pinhole-sized breach in a stainless steel tank can set off a domino effect that takes down the entire system? Detecting and managing leaks in a cryogenic environment is one of the toughest engineering challenges in aerospace. To address this, SpaceX may need to upgrade its welding protocols, reinforcing all critical seams using double seaming techniques, or sealing the exterior with a welded-on metallic film to close off microscopic cracks. Additionally, installing a secondary internal bladder, one that can deploy automatically if the primary tank fails, would act as a last line of defense in worst-case scenarios. Alongside that, the leak detection network must be upgraded to near military-grade precision, high-resolution pressure transducers, ultrasonic leak detectors, and Hall effect-based flow sensors should monitor even the slightest fluctuations. When any anomaly is detected, the flight software should instantly trigger an emergency safing sequence, throttling down the engines, reorienting the spacecraft to maintain heat shield forward posture, and preparing for a controlled splashdown. This is no longer theoretical, it's essential. But Flight 9 revealed yet another critical weakness: Starship's limited control authority during atmospheric re-entry. At hypersonic speeds, The flaps are the only aerodynamic surfaces available for guiding the vehicle. Once the thrusters go offline, those flaps alone aren't enough to counteract an uncontrolled spin. To make matters worse, Ship 35 also failed to deploy its payload bay doors, a core function if Starship is to become a truly versatile spacecraft capable of launching satellites, delivering space station modules, or landing lunar equipment. The issue could have been a frozen actuator, a misaligned hinge, or simply a latch that wasn't strong enough. But regardless of the cause, payload bay door deployment must be absolutely reliable. Without it, Starship is just another heavy-lift rocket, not the symbol of humanity's interplanetary future that Elon Musk envisions. And in engineering, the best solution isn't always the most complex. In fact, true reliability often lies in simplicity. That's why SpaceX engineers are now targeting a redesigned payload door system, one with fewer moving parts, redundant actuators, and fail-safe latches that can be triggered by alternate commands or even by a pyrotechnic device in emergencies. But design theory alone isn't enough. These doors must be put through hundreds, even thousands of open-close cycles inside thermal vacuum chambers that replicate the brutal conditions of space. Did you know this testing approach is almost identical to what the Navy uses for ballistic missile silo doors designed to survive even near nuclear blasts? Still, hardware upgrades are only half the battle. What SpaceX truly needs for Flight 10 is a mindset shift toward integrated testing. Every component, from the booster to the ship to the flight software, must operate as one cohesive system. That means combining actual flight data with fully integrated ground-based simulations that replicate the mission from ignition all the way to splashdown. No system can operate in isolation. Updating flight software is equally crucial. Starship's onboard computers need to be loaded with new failure detection heuristics algorithms smart enough to adapt in real time to unexpected issues, from a sudden pressure drop to a failed ignition or an unforeseen plasma strike during re-entry. Just like the U.S. Navy's Aegis defense systems can instantly shift combat modes in response to live threats, Starship will need that same kind of agility to survive in space. But alongside these technical upgrades, ground operations need a complete overhaul too. With launches planned every 3 to 4 weeks, SpaceX doesn't have the luxury of drawn-out post-mission investigations. Instead, they must streamline inspections using non-destructive evaluation tools, things like ultrasound scanners, thermal imaging cameras, and laser profilometers to assess structural integrity in just a few days. Impressed by the lightning-fast maintenance cycle of an F-35 fighter jet, SpaceX is aiming for something even faster. Rather than spending weeks disassembling hardware, they're shifting to a plug-and-play model, swapping out entire modules, like you would on a military-grade system. And every flight's telemetry will feed directly into an AI-powered anomaly detection system, one smart enough to spot patterns that no human could. This is the same class of technology the U.S. military is developing for next-gen adaptive defense networks. If SpaceX can pull all of this off: tighter tank, sealing, more reliable igniters, smarter flap control, better fire protection, flawless payload deployment, and lightning-fast ground ops, then Flight 10 won't just be another successful launch. It will mark a turning point the moment iterative learning pushed Starship into a new era of true rapid reusability. But what about you? Of all these improvements, which do you think matters most? Which one should SpaceX prioritize first? Drop your thoughts in the comments. We'd love to hear your perspective. From a dusty launch pad in Boca Chica to the edge of the solar system, there have been explosions, nerve-wracking landings, catastrophic failures, and triumphs that made the entire planet hold its breath. This isn't just a story about rockets, it's the story of us. So stick with us here at Space Now. Subscribe, hit the bell, and the next time you hear those Raptor engines roar across your screen, you'll know you just witnessed a piece of history.